بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. So this is lecture 3 in CS316, Introduction to AI and Data Science. And today I'm going to provide you the history about how did we go from machine learning to deep learning. So yesterday we have introduced the difference between AI, machine learning, and deep learning in a broad manner. And today I'm going to give you a few intuitions about the transition, how it was done, and the major works that has led to this transition. So of course, let me just remind that artificial intelligence is the general umbrella, which is quite an old technology, started from rule-based approach to implement kind of expert systems that try to mimic the human intelligence. And in the early 80s, so the problem becomes more and more complex, such that we are not able to determine all the rule in a static manner to capture the complex patterns of the data. And this is where we started to think about, let's try to learn from the data and build the models out of this data. And this is the concept of machine learning. And there are different types of machine learning models, like for doing classification or regression, or clustering for unsupervised learning. We have introduced the different type of learning yesterday, reinforcement learning, another type, and so on. And spam filter detection or spam detection is one of the early applications, classification of pictures, like into different categories. And starting from 2010 and above, with the emergence of neural network and the improvement of the capabilities, the computing and storage capabilities, so neural network have taken the ride and have superseded the traditional machine learning approaches through advanced techniques, because they were able actually to ensure higher accuracy for complex tasks like image classification and later on image detection and recognition. So one of the differences between deep learning and machine learning, of course, when we say deep learning, interestingly, we talk about neural network in the background. And it has been observed over the years that when we increase the data size, so machine learning techniques tend to have a performance that probably reaches certain saturation, while deep learning techniques for very complex problem, they still can increase the performance and reduce the error and improve the accuracy. Of course, here we can see that the performance of deep neural network, it increases with the data size. And now, looking at the history now, we have more and more data every day. Maybe trillions of data are available every day, so this provides sufficient amount of resources to train deep neural network. Because when we say deep learning or deep neural network, we talk about a lot of parameters that we need to adjust. And we cannot have a conversion of statistical distribution conversion unless we have sufficient amount of data to train. And looking even deeper in this slide, so we have different type of neural network. We can have small neural network with a few layers, and today I'm going to introduce the very basic concept of neural network. But usually they are stuck into layers, and each layer do some computation. So when we increase the number of layers, the network becomes deeper, but it requires more data to converge. If you have a deep neural network, very large, and you have a small amount of data, you cannot actually train it very efficiently. You can do that for small neural network, but if you have sufficient amount of data, using deeper neural network with some optimization technique, you are able to achieve, in general, better performance. So let's talk about machine learning and deep learning from the point of view of feature extraction. I already told you that machine learning uses manual feature extraction and deep learning uses automated feature extraction, but we didn't explain the concept internally. And now look at this picture. So everybody, when you see this picture, you know that easily that there is a cat picture. You don't make any effort. Your brain already make processing to identify that this picture refers to a cat. But now let's look at the computer, how it perceives this picture. So a picture is basically a matrix of numbers, like this, between 0 and 255. Now it's not obvious.
إليك ما وجدت.
It is not obvious for a computer program to identify or to extract from these numbers that this is a cat picture. Okay, it's very difficult. You cannot make like rules that try to identify, that try to map this matrix to a cat picture. Because basically a picture is just a superposition of 3 layers of colors. We have the RGB colors, so we have a matrix of red colors, green colors, and blue colors. And every layer, it will have numbers. When you put all of them stacked over each other, so it's going to result in an RGB color. Because every color is just a combination of 3 colors, red, green, and blue. So we can imagine from this that we need a technique to be able to identify that this matrix refers to a cat by extracting its features and processing the features through some classification models.
Each pixel is this one matrix? Or?
Yes. Okay. It's just a matrix, 2-dimensional matrix that contains number, and every matrix, one of the matrices represent the red color, the other one represents the green color, and other one the blue color. When they are stuck over each other, they will provide an RGB image. Okay. So the first thing that we need to do is to extract the features. And what does it mean, extracting the features? So for example, if you have a motorcycle like this, so usually how do I identify that this is a motorcycle? You will see the wheels. There is a wheel, there is a chair, okay, there is a body that looks like a motorcycle. So from the decomposition of this picture, okay, these are represent different features. But now the most important question, how can we extract these features? So the traditional machine learning technique, they perform manual extraction. And deep neural network, they can provide actually automated extraction using convolution, as I will introduce. So feature extraction is the process of transforming this raw data into relevant features. Not all the pixels will contribute equally to the classification of the picture. Okay, so we need to identify edges, we need to identify the colors, we need to identify shapes that will help the computer to decide whether this represents a motorcycle or a cat or a bird or something different. So traditional feature extraction, this is how machine learning works. We have an input, for example, a picture or an image, and we will perform manual feature extraction, handcrafted. And there are different techniques, as I'm going to introduce SIFT technique. What does it mean, feature extraction? Transforming the raw data into just a couple of points, like a digest of the picture. I don't want to deal with the whole picture pixels. I can have 3 million pixels or even more, depending on the size of the image, but I want to make dimensionality reduction. I reduce the dimension to a subset of data that is more representative about the image. Okay, so there have been several techniques that try to make manual feature extraction, and then when I extract the features, couple of points, for example, I will just apply a machine learning model, like for example, Super Vector Machine or AdaBoost, to process this feature, and finally it can do classification, car or not car. So it's not, although it's possible to make the classification over the whole pixel of the image, but it's not very efficient. You cannot get high accuracy because there will be a lot of noise in the image. So we will try to reduce the noise to take only the relevant features and use them to improve the classification accuracy. Is it clear? Okay, so this technique that was proposed by David Lowe in 1999, it tries, for example, to identify the points that are invariant regardless of the position of the image. So for example, here to identify a stop sign, whether in this position or in this position. So there are some points that will be identified as invariant. Of course, we use sophisticated mathematical techniques like linear algebra and calculus to obtain this transformation. So we can transform a picture like this into just a set of points located in that picture, and we use them, their location, in order to identify whether this is a stop sign or something different. So the overall idea is to use transformative techniques. We transform the picture using either statistical techniques or mathematical operation to refine and represent the data efficiently, reducing the noise and only focusing on what kind of data that help me to increase the classification accuracy. Of course, this manual technique, they work, but they are not perfect. I mean, computer vision only started from 2012 with neural network. But before, the best they could achieve like 80%, 70%. It's not something that you can use in production with high accuracy level. Okay, but of course, if we don't use these techniques, we can have 40%, 30%, 50%. So these techniques have been proposed over the years just to try to increase the accuracy as much as possible. Okay, it will also leverage the specific expertise to identify the most informative attributes. For example, here, if we identify stop signs or we identify animals, or, it depends on the domain knowledge. Now, for example, in deep neural network, it's completely agnostic because we don't have manual feature extraction. It will just be based on the data set of all the different pixels that we train on. Okay, and the whole objective is try to improve and enhance the effectiveness of machine learning algorithms. They never become perfect, but if you increase 10%, 5%, over a large number of pictures, you will still have some much better recognition.
ستحتاج إلى فتح قفل الآيفون. ما الذي تود معرفته عنه؟
I don't know why it's stuck in this one. Okay. So another technique which is called the histogram of gradients. So what is a gradient here? It's basically, it tries to identify where the light changes. It's basically the edges. When you see in a picture, the edge, it means a transition between one region and another region. Okay, because if they have the same color, there is no transition, or the transition is very smooth. So when the transition is very high, look now, when the transition is very high, okay, now this is almost constant. We don't have transitions, but here from black to white, it's a high transition. So the gradient are sharp. Okay, so identifying this gradient, we're going to reduce the whole image into just a set of gradient vectors. So this is much easier to take these gradient vectors and use them into a support vector machine or machine learning algorithms to identify. So these gradients represent a feature of the picture. Okay, so I do a transformation of the picture. Instead of relying on the whole pixels, I'm going to rely on the transition between the pixels. So this shape will represent somehow the shape of a standing man. Okay, that could help. For example, see, we try to observe the changes and sort the changes into groups, and then try to smooth out these changes and building a profile out of this gradient. Okay, so there was an improvement by McAllister in 2009. It's called the deformable part model. And basically, it uses the same Hogg technique, the histogram of gradient, but instead of working on the whole image, it's going to divide the image into regions, extract the histogram of gradient, and then assemble all of them together. These are just different variations, trying to improve the accuracy with a few percentages. So this technique, they were emerging up to 2010, 2009. And in parallel, there was also the development of neural networks. So neural networks started from maybe early 60s, 70s with the basic theory behind it. And what is a neural network? It's basically a linear transformation of the features. Now, imagine that you extracted features. There will be numbers at the end. So everything in machine learning are just numbers. This is why we transform any kind of data into numbers, into vectors. And this is why we need linear algebra. So an image is a vector, a text is a vector. Everything in machine learning and data science is just a vector to make predictive models. And this is why linear algebra, we're going to use it. It's not very much advanced. We need dot product, we need a few concepts. But this is why it's really needed. So now imagine that we have features here. They can be raw pixels or maybe features. And what we will do, we're going so we have weights. A neural network will consist of weights, W1 and W2. And you're going to calculate an output Z equal to W1 x1 plus W2 x2 plus B. It's just a linear transformation. But it was observed that linear transformation is not sufficient to learn a lot of features. So this is why we add a nonlinear function. The nonlinearity will add additional benefits to improve the learning capabilities. Because if you transform anything linearly, it will be proportional. So there is no big variations. So for example, there are different techniques like using the sigmoid function, tan H function, there are ReLU function, there are different nonlinear functions that we can use applied to the linear output. So later on, we're going to calculate a value, an output value. And here, we don't forget that we use a supervised learning. What does it mean, supervised learning? We have the input and we know the output. Now imagine that I calculated this value, I will find an output. So what I will do? I will compare the output I found from the network with the real output because I have a labeled data. Okay? So here it will result into a loss or what we call an error. Okay, so when I have an error here, what does it mean I have an error? It means that these weights are not correct. Okay? So in order to minimize the error, imagine that you have a convex function. How to find the minimum? What is the minimum of a function? Yeah, the derivative is 0. We will do the same thing. We will make the derivative of the error over the weights and we will make it equal to 0 to find the new weights that will minimize that error. Okay, so this is over one sample and we take another sample from the data set, we do the same thing. So we will make a first pass of whole data, always try to minimize the error, and then a second pass, third pass, until we try to minimize the error over the whole data. So when the error is close to 0, it means I will have a good accuracy most of the time.
How do you find the weights?
So the weights, in the beginning, it's random. You can choose random weights. We can put them 0, we can put them small random variables. So there are different ways. Okay? And the objective here is to calculate the loss of every pass. This is what we call forward propagation. And then we're going to calculate the derivative back, trying to update these weights such that when I do another iteration, the loss is smaller. This is why we will find the loss going down, 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 until, okay, in the perfect way, it will reach 0, but it will never reach 0. I mean, if you have a loss 0 point something or 1 point something or so on, that's something that could be reasonable. So a neural network, and this is what we call the perceptron. It's only one neuron, but a deep neural network will have thousands or maybe millions of neurons like this. They will do always the same computation. It's basically some, and you know, if we put this in a matrix form, it will become a dot product between a matrix x1, x2, this is a vector, multiplied by the matrix of the weight, will be equal to the matrix Z. Okay, just to put all the features together as a matrix or as a vector instead of doing the, and this is like a matrix representation, Wx plus B. Okay, it's a linear transformation, and then we apply nonlinear function to do that. And this is the error. Don't worry about it. This is called the logistic error. We're going to have full lecture about how to calculate this. Yes.
How do you transform the function from linear to nonlinear?
How do you transform? Yeah. Now, for example, here, this is a function that is called sigmoid. It transforms every value between 0 and 1. And usually we use sigmoid when, for example, our output is a probability. Okay, imagine that you have a classification, you want to classify whether an image is a cut or not a cut. So usually we're going to rely on a probability. If the probability is higher than 0.5, we will say this is a cut. If it is below than 0.5, we will say this is not a cut. That's one example. Of course, it has several usages. That's one of the examples. And there are multi-class, a function for multi-class classification and so on. But don't worry, you know, the most important thing is just to understand the basic concept. Okay, I want to give you some flavors. And you know, this has been using in machine learning because the problem is how to identify these features. Now, if I cannot identify these features, either I calculate them manually, or for example, if I have a picture, I will just use all pixels. So let's go back, for example, to a picture like this. Okay, we need to calculate the features. And for these pictures, usually when we want to train them into a neural network, we need to put them as a vector. So I will take just the pixels one by one and stack them over a vector. This is one of the possible ways on how we can provide an input of neural network. Or I try to make for example, machine learning technique like SIFT or the histogram of gradient in order to reduce the size of the picture into a much smaller feature vector. Okay, so we want to create a feature vector. Now we can take the whole pixels, that's the possible way of a feature vector if we consider every pixel is a feature, or we can use other machine learning techniques to manually extract the feature in some of the ways. But at the end, the most important thing is that the input to a machine learning model or to a deep learning model is just a vector like this. And you know, this is just a very simple representation. Now if I have a picture like this, contain features or pixels, I will stack them one after the other. This is the matrix of the weight. I will make W multiplied by X plus a certain vector, and this will give me some scores. And how can I do the classification? Look, I didn't do here the sigmoid function. Sigmoid function is going to transform these numbers between 0 and 1. Okay, let's assume they are probabilities. I will consider that the biggest value is the most likelihood. I will come to you. So now, if this function is, we see that this picture is not a dog, so there is an error. We're going to calculate the error and try to minimize the error in the next run. Yes?
البكسل ما يكون بكسل حجمه كبير يعني.
No, the pixel is just a unit of a picture. And the picture is a collection of pixels, and every pixel has color.
يعني بالفيكتور راح ياخذ البكسل.
Yeah, this is just we can call it pixel or features. Okay, so we have an input which is a feature vector.
وراح يسوي له مقارنه مع الويت حقها.
Yes, so now if this image is labeled, you know it is a cat. Okay, and here if the prediction is a dog, you know that there is an error. So we're going to change this weight in order next time when I calculate on this picture, I will find that the score of the cat will be higher than the other scores.
الويت راح يكون صور الكات.
الويتس لا، الويتس these are parameters اللي هما represent the model, represent the transformation of the data into the output. And what we said, what is machine learning? We try to build the function. So what is our function or our program? It's the weight and the bias, which we call the parameter of the model. Okay, and this is the input, we call it the feature vector. Okay, so since we don't know how to calculate these matrices in a static manner or in a manual manner, we're going to rely on optimization techniques to reduce the error in every iteration. Okay, and at the end, when I reduce the error as much as possible, I have a reliable model that is represented by the parameters of the weights and also the bias. We call this a bias vector and the weight vector. Don't worry about the terminologies right now. It's just a function, okay, that will capture the model capabilities to do the classification. Well, we're talking at the very high level surface. Okay, yes.
The weight and the bias is going to be generated from the program or the function.
In the beginning, they are random, and they will be updated with every data. This is why when you have a huge amount of data, you will do much more optimizations and much more updates. And at the end, it will make a convergence. Of course, I'm going to make you a refresher of some statistical concepts. You will understand why at the end this model will converge. Okay, yes?
Doctor, what I understood from this is we're using the previous scores just to update and get optimization
Yes.
for the new way.
Yes. So optimization, it means improving the model accuracy
Yes.
and reducing the model error.
Yes.
And this is done using derivative, as you already mentioned. Derivative equal to 0 give me the minimum of the function. Of course, all these concepts, we're going to learn them in detail. So later on, when you do any deep learning model, you know 100% what is inside. You will see a deep learning model as a white box, not as a black box. Okay? But just now, we introduced this concept. Now we understand that the neural network model is just a matrix of weight and bias. That's finished. And we need to find the best combination of these weights to provide the best performance. That's it. As simple as this. And of course, this is one neuron. Imagine that you have millions of neurons into a model. Like ChatGPT, it has 1.5 trillion parameters, ChatGPT 4. Trillion parameters that you need to converge to some values. Okay, so we have reached now very, very big model, and now we're talking about 5 trillion parameters and even more for the new generation of large language models that are coming. Okay, so that's one perceptron, but usually when we have a lot of classes, cats, birds, or different type of animals, we can go even deeper. For example, we can have 1, 2, everyone is perceptron. This operation is done by only one node. Okay, only one neuron. And this is one layer, then another layer, then another layer, until at the end we'll calculate probabilities. We can apply sigmoid function to have, or softmax function for multiclass in order to find these probabilities. Okay, but now the most important problem again is in terms of the features. Extracting this feature manually is not very efficient, and using the whole pixels is not very efficient either. So the community have worked on how to extract features manually, and there are two main operators in what we call the convolutional neural networks, is the convolution and the pooling. And what is feature extraction? It means I will go from high dimension, large image, into smaller dimension, reducing the dimension, try to digest the images into smaller sizes that are more focused on the features. So what does it do, convolution? Very simple. It will take a filter. So this filter it has also weights that must be learned. Okay? In the beginning, is going to be random. And same thing, we're going to multiply this matrix by this region of this is the image. This is the input image. And applying these features, so look, you have 3 by 3 multiplied by 3 by 3. So I'm going to reduce this region into one number. I reduce the dimensional. Okay? So it's like I'm digesting the picture into smaller size. Of course, this is random. So in the beginning, it's going to extract wrong features. And we use the same technique, calculate the error, going backward, derivative, refining over iterations. But it turns out that this way is going to reduce the pictures over different layers. This is why we need many layers when we have a lot of images. And it will reduce the dimension to smaller size. Now, also, another technique is called, now imagine that I made a convolution, I obtained another, this is what we call feature map. It's a matrix that represents the features. We call it feature map. And this feature map, we're going to apply other operators, usually what we call pooling. So these numbers, they represent kind of the luminosity of the pixels. So what we will do, we have two options. We take the highest color, so the highest brightness of the pixel. This is what we call max pooling. Or we can take the average. It's a way to reduce the dimension even more. Okay, so instead of having 4 pixels, 29, 15, 0, and 10, I will say this is 100, or 0 and 100, I will take just 100, the maximum. Okay, so, or the average pooling, saying I can take the average of all of this, so I will replace all these 4 pixels by 1 pixel that is 36. We apply these operations, yes.
So what's the difference between providing, in this case, an image, which is from the start low quality, versus convolution producing an image of...
Yeah, because convolution, as you go deeper into the layers, you're going to start from 10 million pixels to a vector of 1024. So it's like calculating a summary of the pictures over the layers. It's kind of magic. Okay? Magical. But it works. So with the iterations, with the optimization that we do, reducing the dimensionality over the layers, okay, every layer is going to extract some features. Until the last layer, we'll have the most digested summary of all these features. And then we're going to apply it to a neural network like I presented before. So instead of just inputting the raw pixel here, I will go through several iterations here and finally apply it to the classification. And this is why this is a typical convolutional neural network with automated feature extraction. So I have two parts here. So this is the neural network we've talked about, and which was used before in the era of machine learning, what we call the classification head. You have an input vector, it will classify that vector. But now the only difference, instead of using the image pixels directly, is it's going to go through what we call the feature extraction module. And this feature extraction, this is what is going to be deep. Okay? So, for example, AlexNet, the first one that was proposed in 2012, it has 8 layers of convolution. And then a couple of layers, 2 or 3 layers for classification. Of course, it was applied on MNIST dataset, and then also on ImageNet as well for classification. So look at this. So all of these are convolution and pooling layers. They are going to reduce the dimension from one layer to another. Of course, this depends on the filter size, what we call the kernel. It depends on the pooling type. Okay, but when it comes deeper, you're going to digest the pictures, and every picture in this layer is just a feature map. And this feature map is going to be converted into a vector, and then we apply the classification. Okay, this is just an overview about how we reach into CNN and why it took a lot of importance over the community. Look now. So back in early 2010, there was an ImageNet challenge, which consists in classification of pictures over, I think, 1,000 classes. So before neural network, this is where AlexNet was proposed. So the best they were able to achieve is an error of 25%. And look, every year they only reduce 2%, 3%. So from one year to another, there was no substantial improve of the accuracy or reduction of the error. But suddenly, in 2012, AlexNet used convolutional neural network, and they were able to decrease from 25% to 16% of error. That was booming, making 10% of accuracy improvement is huge, is really huge. Okay, that was abnormal. From that time, all the community were working like ChatGPT. Everyone is working on ChatGPT and NLP and so on. People were working on improving convolutional networks. They started from AlexNet, and then in 2013, they provided VGGNet here by Microsoft. There was also, I forget different names, VGGNet, AlexNet, ResNet in 2015, also by Microsoft. And ResNet achieved 3.75 error rate, which has improved over the human perception on that dataset. So that was the first time where the AI was able to beat humans in the classification of pictures, the manual classification of pictures. Okay, and this is due to leveraging the automated feature extraction using convolution. Of course, convolution, they have tried to come out with different type of architecture, with different type of techniques, optimization in terms of computation and so on, until they were able to reach this capability. Okay, and that was 2015, just around 10 years ago, where they reached this type of performance. And of course, this has opened the horizon to later on also introduce object detection, not only classification, using YOLO, faster RCNN, and these type of models. Now, let me go through a summary. Okay, so computer vision has evolved from pictures like this, and we went from machine learning, which is a manual feature extraction, to automated feature extraction using convolutions. And then we have the image classification with the ImageNet challenge that has made substantial changes to the community. And from there, people have been working on several new type of problems. Like, for example, this is classification, that everything that I've talked about, just to classify whether this picture is a cat, is a dog, or something. But later on, it has evolved to a more complex problem, that is classification plus localization. So I classify this is a cat, and the cat is located into these pixels, the bounding box. And then object detection. We try to detect every kind of object into the image. So this image contains a dog, a duck, and a cat. Okay? And also we have instance segmentation. It means we don't only detect the bounding box, but the boundary of the picture, of the image, and this is even more challenging. And after this, we have segmentation. It was used in self-driving cars just to identify the regions, the drivable area, the obstacle type. We want to categorize. I don't want to deal with every detail in the picture, But for example, this red color represent pedestrians, this blue color represent cars, this is a drivable surface, and based on this, we can take better decision from a segmented environment. Other techniques like domain adaptation, because sometimes when you do classification on a domain, for example, if you classify buildings in Riyadh, you have a model that classifies building in Riyadh, you want to apply it in Europe, it's not the same landscape. So the accuracy will not be the same. So domain adaptation try to avoid retraining a model by trying to adapt the model to new conditions. This is for image captioning, deep fake. So this is the start of generative AI, where with deep fake that is able to generate videos, completely fake videos out of the people. The famous Barack Obama videos is available on the internet. And vision transformer. So of course, transformer, it comes from the NLP community that has provided the large language models, and later on it was applied on the vision. Just in a nutshell, vision transformers, instead of using convolution, it just divide the pictures into patches. So the picture will become like a sequential model, like a text of 16 patches. And then they use a technique that is called attention, which help to improve the accuracy of detecting like substantial features into the picture. But of course, it's only Google that were able to find something that beats the ordinary convolutional network models, because it has used a huge amount of pictures that nobody else have. And they built the vision transformer model that is pre-trained, and then it was used by the community. And of course, now we have text to generation. We talked about diffusion models using generative AI. So on the other hand, just to give you a brief overview about natural language processing, NLP. So also it has evolved over several techniques. 2003, there was a neural language modeling and word embedding. Word embedding, it means we will convert a word into a vector of numbers. And of course, we don't convert it into any random manner. So usually when we do embedding, we try to have the vectors very close to each other for the word that have close semantics. And how do we know that two vectors that represent the word are close to each other? How do we do that in linear algebra? For those who did linear algebra. The dot product is equal to 0. It means the two vectors are identical. So when the dot product is close to 1, when the dot product is close to 1, they are equal. And if the dot product is 0, it means they are orthogonal. It means 0. So if I convert two words into vectors, and I make sure that if the two words have similar semantics, the vector will be close to each other. So this is how we do semantic search. Now when you search for a word on Google, it's going to convert your query into a vector, and then it will have a vector database where it searches the closest vectors to your query. This is what we call semantic search. This is possible through the word embedding. And 2015, there was also the proposal of attention, several type of applications, text classification like sentiment analysis, spam classification in emails, social media analysis. This is very popular. So plenty of works. And in counterpart of convolutional neural network, since text is sequential data because it has a logical order between the words, so we use sequential models, which we call the recurrent neural network. And it has different variations that we call LSTM and GRU, but all of them, they belong to the same family of recurrent neural network. They are able to process sequential data that comes as a sequence. Like a text is a sequential data. A video is a sequential data. A voice is a sequential data. A DNA is a sequential data. Okay? So all these kind of sequential data, a time series is a sequential data. They use this type of models. Until 2018, people have come up with transformer using attention. Using attention, and this has led to the proposal of ChatGPT, large language models on a different type of these models that we see nowadays. Okay, I think we reached to the end of the lecture. We have only a few slides about data type. that we will start next time, inshallah.